Hi kiddos, and welcome to part 2 of our bonding. So last time we learned about certain things like what a bonding electron is, what a lone pair is, where orbitals kind of exist. So now what we're going to do is we're going to take that and go a little further, and we're going to draw these electron dot diagrams, but we're going to use them for actual molecules. So when we have different amounts of things coming together. So let's look at the objectives for today's lesson. We're going to draw electron dot diagrams of atoms and molecules. We're going to look at something called the structural formula, and we're going to predict bonding in simple molecules. We're going to look at just different ways of drawing these molecular things, and also we're going to take a look at what ionic substances look like, okay? All right, so let's take a look at molecular elements. Many molecular elements are diatomic. Remember that? Where they're always paired up, like oxygen, um, hydrogen, nitrogen. So these are all your diatomic elements. See, they all have a subscript of 2. Be aware that phosphorus has a subscript of 4, so it's always P4. Phosphorus doesn't ever exist by itself. And sulfur is S8, which is awesome because sulfur is so complicated, remember? All of these, as you recall from Science 10 or even in grade 9, they all have to do with the fact that they can't exist on their own. They have to be, in order to become stable, they have to pair up with itself, another version of itself, okay? So hydrogen is always, always, always H2. And the way they look like varies in terms of real life. But what you have to know how to do is just draw them together in terms of a Lewis dot diagram. Okay, so why are they diatomic? Because they each have, most of them are in group 17, so they each only have, most of them anyways, 7 valence electrons, and these are for the diatomic. So as you can see here, fluorine, because this fluorine has only 1 bonding electron, and this fluorine has 1 bonding electron, what's going to happen, kiddos, is that they are unstable by themselves, but when they come together, it almost fits like Lego. They'll come together because there's room here and there's room here, so they're going to share, and remember, these are going to have the same En number, so they're going to share that electron. They're going to share equally. So this is how you draw it. Together, you're going to show that this is where they share. So they've come together to essentially fill each of their half-full orbitals. Now, this is the Lewis dot diagram, and this here is the structural formula. All you have to show for that is you use a line to show a bond, and you don't have to include your valence electrons, your dots. Now, what you can do for a Lewis dot diagram is you can actually do it like this too, where you just show the dots where they're not bonded. So this and this are the same. When I'm asking for the structural formula, we do not include any dots. We just simply include a line to show the bond. This line here shows a single bond, and what a single bond represents are just 2 shared electrons. Okay, kiddos? Okay, so these are still just models. How about oxygen and nitrogen? Now, these are a little bit more complicated because in this case, they're not found in group 17, so they don't have only 7 valence electrons. So let's just take a look. Here we have oxygen. Take a look at what's going on with oxygen. Oxygen has 2 lone pairs, lone pair number 1, lone pair number 2, and we have 2 bonding electrons. So when I put another oxygen beside it, what's going to happen is that this bonding electron is going to pair up with this bonding electron. This bonding electron is going to pair up with this bonding electron. So when I draw it out, you'll notice that here is my bond. You'll see that there's 2 bonding electrons each. So this is a double bond, kiddos. And remember with the rules of how electrons work and stuff like that, that's why these lone pairs are pushed away, because they try to separate as far away as possible. I'm not really picky right now about where you put your electrons as long as the number of dots are correct. But down the road, when we learn about VSEPR diagrams, that's where things become really important. So here's your structural formula. Here's that double bond. That represents two sets of shared electrons. And remember, with the structural formula, you don't include the lone pairs on the anywhere in the diagram. So here's nitrogen by itself. Now, if you take a look at nitrogen, you'll notice that there's three bonding electrons and one lone pair. There's our lone pair. Remember, with a lone pair, you can't bond to a lone pair because it's full. And here we have three bonding electrons. If I have another nitrogen right beside it, because this is very unstable, it's going to have to stabilize by coming together, kind of like Legos. So these two will come together, these two will come together to fill, and they're shared equally, right, because they have the same En numbers. These are going to come together to form a triple bond. So there's your Lewis dot diagram, and there you have your structural formula. These guys are all called, oops, I'll go back here. We call these a triple bond and a double bond. They're so called multiple bonds. So if there's ever an assessment where it says, oh, how many have multiple bonds in chemistry doesn't mean lots of bonds. Multiple bonds in chemistry means doubles or triples. Okay, so let's just clarify that. It's in the program of studies. Okay, so here's an animation for Cl2. There's the sharing of electrons. There is the structural formula. And remember, when you're drawing the Lewis dot diagram, we do not include any of the interior electrons. We don't include those. Okay, here's our Lewis dot diagram, and here is our structural formula. You need to know both, kiddos, and then later on when we learn about VSEPR diagrams, you have to draw it a different way yet again. But it's really fun. There's oxygen. Each oxygen has two lone pairs and two bonding electrons. So what's going to happen is those bonding electrons are going to come together in order to stabilize the molecule. So here again is the structural formula, and here is the Lewis dot formula. And then we are also what you are responsible for as well is drawing out molecules. So let's take a look at oxygen. Oxygen has, here's one bonding electron, here's one bonding electron. There's no bonding here. Those are lone pairs, right? So what's going to happen, kiddos, is this bonding electron is going to come together and they're going to share here so that everyone's happy. So there we go, and there is our Lewis dot diagram, and here is our structural formula. So let's talk a little bit about molecular compounds in general. They have covalent bonds where electrons are shared. Sometimes they're also called molecular bonds, but we're going to use the word covalent bonds. But like I said, if you see the word molecular bonds, it's not wrong. And it's between two nonmetals. They can be solid, liquid, or gas at standard ambient temperature and pressure. So at room temperature, they can be solid, liquid, or gas. There's really no way of predicting-ish. So I won't test you on that because it's really hard to predict. May or may not be soluble in water. We'll learn about that later. You will be able to predict if something's soluble in water or not in a few classes. And they don't ever conduct electricity, even when they're dissolved in water. That's what AQ means. Never, ever. They generally have lower melting points and boiling points when they're compared to ionic substances. And let's continue. We take a look at their empirical formulas to show the simplest whole number ratios of atoms in a compound. That is only helpful for ionic compounds. Remember, with ionic compounds, they exist in a crystal lattice. Well, if I were to, this is NaCl, if I were to count out all of the sodiums and chlorines, it's very probable that I get a large number. But for our ionic substances, we're like, listen, this is too much. It's too much. So we're going to simplify it. And you see how it's a 1-to-1 ratio? That's why NaCl There's only a 1-to-1 ratio here. We can't do this for molecular compounds. For molecular compounds, this type of empirical formula is not useful because when you change the subscripts, okay, it actually changes the substance itself. Not only does it change the substance itself, but it also, these three, for example, have very, very different characteristics. In ionic substances, for sure, we always take the lowest possible ratio. Okay, again, what characterizes the most about what a molecular compound is: two nonmetals, two or more nonmetals together. And we also take a look at the fact that electrons are being shared. And remember, depending on the EN number, they may not be shared equally. Sometimes it's a polar covalent molecule or a bond where the electron shifts to the element that has the higher EN number. Okay, another thing too is both of these ways of drawing are completely acceptable. On a test or on an assessment or homework, I won't give you this one very often. Like if I do, it's just to show it to you, because this is the better way of showing what a molecular compound is, because it gives you a roadmap. It kind of shows you what to do. So here we have an example of a molecular drawing in terms of the Lewis dot diagram. This is a better roadmap. So what does it tell you? It tells you the first element is carbon, right? Carbon has 4 bonding electrons. The next one is hydrogen, and there's 3 hydrogens. So you go ahead and draw the 3. Hydrogen, 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 right? Then we have carbon. So now I'm going to throw a carbon in there, and you'll notice that right beside a carbon is an oxygen. So if I were to draw oxygen here, I would have 6. Notice that there's 2 bonding electrons, and carbon has 4 bonding electrons. So right here, these guys are going to come together. These guys are going to come together to form a double bond. And I still have a bonding electron, but that's okay, because I still need to put in an oxygen and a hydrogen, right? So I can have my my oxygen here. 1, 2, 3, 4, 5, 6. These guys come together, and you see this little guy? It's fortuitous that there's a hydrogen here, because that's where my hydrogen goes. I can't follow this to get that if I'm using this configuration. It's not wrong, it's just not super helpful. So we're going to do a lot of these. Okay, so empirical formula, of course, is incorrect. So let's take a look at the different ways we can use formulas to inform ourselves of the molecular compound. We have the empirical formula. We don't use that. Oops. I have the empirical formula. We don't use that so much. Okay. We have the molecular formula, which both of these are correct, but this is your better way of using in order to figure out how to draw your Lewis formula. And if we had to show a structural diagram, all you're doing is you're just showing, using a line, where your bonds are. Okay, so that's a structural formula. You don't use you don't include any of the lone pairs. Okay, how do we know how molecular compounds bond? Basically, where do they come from? We have to take a look at the bonding electrons that are available to us, and we take a look at the lone pairs. You can't bond where there's a lone pair, and you can't bond, kiddos, where there's an empty space. Okay, so here's just some examples. And let's take a look at something called bonding capacity. Bonding capacity is going to match exactly the amount of bonding electrons. So bonding capacity is the maximum number of single covalent bonds that an atom can form. And if you take a look, how many electrons does an atom want in its valence electron level to be satisfied? We want to make sure that using shared electrons, including shared electrons, we have 8 total, okay? Reminder, what types of covalent bonds are possible? We have single bonds where you only share one pair of electrons. You have something called a double bond, shares two pair of electrons, and then you have something called a triple bond where you share three types of electrons. These, remember, doubles and triples are called multiple bonds. Why do we care about bonding capacity? If we know how many bonding electrons we have, we know how many times things can bond. See, notice here, these are the total number of valence electrons and the total number of bonding electrons, right? And then for total number of valence electrons, obviously when we draw it out, some of them are going to be lone pairs. These two numbers match. Your number of bonding electrons matches your bonding capacity. Okay, here's an example. Carbon dioxide. If I were to draw carbon dioxide out, you'll notice that you want to have those bonding electrons match out. So carbon dioxide is going to have two double bonds. If I were to draw them out separately, sometimes I like to draw things out separately, so it gives me an idea of what I need to do. Notice I have 4 bonding electrons, right? So I can even show you that I have room for one more in each of these spaces, whereas oxygen only has 2 bonding electrons, right? So as you can see, here we have 1 and 1, and then these guys are going to come in over here. So we're going to essentially have 2 double bonds between the carbon and the 2 oxygens. Here's an example of cyanic acid. Here are 4 bonding electrons and 3 bonding electrons. You can see where this is going to go, right? So this guy's going to go here, this guy's going to go here, this guy's going to go here, and here's 1 bonding electron. So when they all come together, you can simply use, this is a Lewis dot diagram because you still have it shows, if you include these lone pairs, it's a Lewis dot diagram, this is a structural diagram, okay? Okay, so now what I'm going to have you do is take a break. So you're going to pause this podcast, and I have assigned some work for you to do, and then I will see you back in about 25 minutes, half an hour, and then we're going to move on with a different strategy of how to draw these diagrams. So we're going to take a break, and I'm going to then have part 2 of the podcast,